Thank you so much for having me. I'm delighted to be here today. And just to get kind of a feel for the audience, how many of you guys are doing data science or machine learning for your day job? Okay, cool. How many of you are interested in data science or AI and applying it to your company or your current role? Awesome. And how many people are here because you maybe saw a salary posting for data science or machine learning and got real excited? Awesome. So just want to make sure, can everybody hear me? It sounded a little bit soft from the back. I'll move up my microphone a little bit and hopefully that'll take care of it. But yes, so I am Paige Bailey. I'm a cloud developer advocate at Microsoft. My background's a little bit wonky for the tech industry in general. I did an undergrad in geophysics and applied math, and then I did grad work in computer science and in carbonate geology, which is the study of reefs. So completely atypical for playing around with electronics for the every day of the week. My first computer actually was an Apple II, so nerddom started around age 8, very early. And as was mentioned, I have a lot of experience with Python, about a decade, R, half a decade, and some open source tooling specifically designed for large-scale data processing like Apache Spark, and then also some things like Hive and HBase. And I'm based here in Bellevue, so if anybody has any questions, if you're local, I'm always happy to meet up for coffee and talk to you about Azure or about machine learning or careers or whatever. I'm also Dynamic Web Page on Twitter. So feel free to contact me there. I'm Dynamic Web Page pretty much everywhere else on the internet as well. So all of the code samples that I'm showing you today, they're on my GitHub, and it's Dynamic Web Page too. So today, a little bit of a roadmap. We're going to discuss what machine learning is in general. So we got a pretty good overview of it this morning, but it's still a lot of terminology. So for folks that are just starting out, I'm going to try to make sense of all of the jargon. We're going to talk a little bit about how it's used and the variety of ways that you can do machine learning in cloud-based environments. Even if you don't necessarily have experience with Python or R, you don't necessarily have linear algebra background. And then also, how can you scale out models? So models that have either already been created or models that you're in the process of training, retraining, and deploying yourself. So for starters, what is artificial intelligence? And the textbook definition, so if you opened up a copy of AI, A Modern Approach from Peter Norvig, or any of the other deep learning textbooks, you'd see something that says any technique that enables computers to mimic human behavior. And based on that definition, AI's been around for a long time, like since the 50s and 60s, when it was called symbolic AI. And back then, there was this idea that you as a developer had to be responsible for explicitly coding every single if-else statement that would be required to make a machine function in an intelligent way. So you would have to have data as inputs. You would have to say, all right, if Paige says, bring me a cup of coffee, robot would have to do, however many thousands of steps in order to make that happen. And since then, so since that 1950s, 1960s era of symbolic AI, we've moved a little bit further. So we've realized that it's not really feasible for you to be able to hard code every single explicit statement into an intelligence. So we've got machine learning. And machine learning is where it starts to get a bit more interesting. And machine learning is the ability for a computer to learn without being explicitly programmed. So what does that mean? If you took a programming course in college, again, you have data, you have code, so if-else statements and other functions that you explicitly type, and then you get some sort of output. So your program is responsible for producing some output. For machine learning, it's a little bit different. You have input data, and you have what your expected output should be, and then you give both of those things to a computer, and it gives you back the if-else rules. And if you're lazy like me, that's really, really exciting, because instead of me having to know precisely every single pixel configuration that could possibly comprise a cat, like the computer just figures it out for me if I give it enough example data. So that's really, really cool. And machine learning, again, it's been around for a while. So if you open up a 90s textbook on machine learning, you can see pretty much a tree similar to this guy, right? So if you have labeled data, if you have data that you know what it is, it's a picture of a cat, you called it a cat, it's a bunch of characteristics, and you know that they are for a Democrat or a Republican voter, then you start with that labeled data, and then you do either a supervised learning problem or an unsupervised problem. And if it's if it's a supervised problem, your data's been labeled, and you can either do categories or quantities. And a category, a classification problem, would be kind of like taking a picture and doing that, this is a cat, this is a dog assessment. Or again, it could be taking some input data and saying this is a Republican or a Democrat, or this person defaulted on a loan or not. A regression problem is trying to predict a numeric value, some sort of quantity. So I'm going to sell 7 widgets in June of next year, right? Like that would be a regression task. And there are a variety of algorithms associated with each of those things, right? So you have things like support vector machines, classification and regression trees, least absolute shrinkage and selection operators, I think that's what it's called. And then also things like linear regression. So if you're familiar with Excel, and you pull in data to Excel, and you do right-click scatter plot, and then it puts in a line of best fit, well, congratulations, you've been doing machine learning. Because that's really all it is. It's taking an input and predicting an output. And that's all y equals mx plus b is. You get an input, and it produces an output. If you don't have labeled data, then life is less friendly, right? It means that you have to do something like clustering, which is very difficult to do because you don't know the answers ahead of time. You're just kind of exploring through your data to see if you can find some sort of relationship. And most of the work that's been done in machine learning and AI to date has been on those classified problems. That's why you see things like Mechanical Turk kind of taking off, where if you're not familiar with it, Mechanical Turk is people in the background, like you give a task to AWS, and then people in the background hand label images or hand annotate certain things. And even though it's something that you can order as a cloud service, it's all kind of people doing that classification stuff. But the reason why that's useful is because if you have a classification problem, so your data's already been pre-labeled, they probably take like a month. Whereas if you have an unsupervised problem, you don't have labeled data, then it'll probably take more like half a year to get things correct. And there was a great tweet a while back saying something to the effect of, it's better to employ an intern for a month to hand tag data and to have a classification problem than to have a machine learning engineer devote 6 months and a whole bunch of elbow grease and a lot of training to do an unsupervised problem. So that's kind of the typical machine learning breakdown. But that's also a lot of words on a slide, and it might be a little bit confusing. So I love examples. Let's try an example, right? So say your boss comes to you with a CSV file, because it's always a CSV file. And engineers speak in CSVs. But he says, okay, we have all of this information about our customers. We work at a bank, and we have their age, we have whether or not they have a job, whether or not they own a house, their credit rating, their education, and then whether or not they defaulted on a loan or not. So whether they paid us back on time or if they went bankrupt, if they were no longer able to. And really, if you're my boss and I work at a bank, all you care about is that last column. So did somebody give me my money when they said they were supposed to? And really, what you care about is the likelihood of a default from this new potential customer, this 35-year-old who has a job, who doesn't own a house, who has bad credit, but who went to college. Is this somebody that I should take a chance on giving a loan to? Is this somebody who has a high likelihood of paying me back? And you can do something like build a decision tree, which probably looks pretty familiar to everybody in the audience. You have a node, and it has a question, and then you just kind of follow it down like a choose your own adventure book. And then you have, if you follow this flow for a decision tree, which is an example of a machine learning algorithm, you can see that this person who's in his 30s, who doesn't have a house, but who did go to college, should probably be given a loan. There's a high likelihood that he would pay us back. And this all seems very, heuristic-y, right? Like very defined rules. So how easy is it really to create something like this with machine learning? And I'm of the opinion that nothing really exists unless I show you code. So let's go and take a look at it right now. And if I bounce over to this guy, that's spoilers. So we will see this. We will see that soon. But this is something called Azure Notebooks. So notebooks.azure.com, and it is an open source or free rather implementation of an open source tool called Jupyter Notebooks. Has anybody ever seen Jupyter Notebooks before? Several hands? Okay, cool. So that is your homework. Like, I don't care if you don't listen to anything else I say for the rest of the day. Like, go to notebooks.azure.com and try out Jupyter Notebooks because they're the coolest thing. And like I said, they're completely free. They're an open source tool. And they were recently awarded a very prestigious prize from ACM, which is one of the top computer science organizations. But what it is it gives you the ability to open up a notebook environment and to dynamically program in each one of these cells and to immediately see a response back. So if I double click here, it automatically goes to Markdown. I can edit it as I want. So if I want to include a cloud, let's see if Markdown can render clouds. Maybe it can, maybe it can't. Maybe I'll crash my computer. There it goes. Awesome. So, so you can change Markdown. You can change all of the code in the cells. And it immediately spits back a response underneath that cell. So here you can see I'm importing a CSV file, and then I'm checking out the structure of it. This is using R if people aren't familiar with the language. And it can tell you this CSV file with all of that information about our customers has been pulled in, and it has these kinds of types. So factors versus integers versus whatever. And whenever I use the word feature for machine learning, I want you to think of a column in an Excel spreadsheet. And whenever I say record, I want you to just think of a row. So feature, column, record, just a row, just another human being that's been included. So we have 1,000 observations, 1,000 records, 1,000 rows of 17 variables are features, 17 columns in that spreadsheet. So we keep going down. We can get some information about what our data looks like. We would divide that up into a training and a test set. And then to train the model using R to build this machine learning model of a decision tree with all of those nice branching questions that we were discussing before, it's one line of code. So it is that guy right there, the credit model C5.0. Credit train, just removing one of the columns and then training on the rest of them. And that's kind of magic to me. Like that's why I love open source, because hundreds of thousands of people, most of whom are smarter than I could ever hope to be in some of this stuff, who have devoted decades of their lives to researching these hard problems, have out of the goodness of their hearts open sourced these great packages for machine learning and for deep learning. So you can use them as easily as you could use any other thing on Azure. And it's all just kind of leveraging the compute capacity of the platform. So once that's been run, so once that one statement has been input, you get back something that looks like this. And it's just a less pretty version of what I had shown you before. It's, like each of these little branching statements are one of the questions, and based on the answer to that question, you get classified as either a yes, you're going to default, or a no, that you're not. And then you can do things like evaluate model performance, check to see what how accurate your model is, and here it looks like with just that one try, we have an error rate of 13%, which is much better than just like a coin toss of yes or no, right? So that's kind of awesome. And again, this is completely free to run on notebooks.azure.com. It doesn't have a GPU on the back end, but it has a CPU. And it's a pretty quick task. So if we go back to the slide deck, and we start thinking about like, oh man, I'm gonna go sell my house and learn me some machine learning or something, or how do I download machine learning to my computer or whatever. I want to give some caveat statements for this, right? So machine learning can be problematic for a number of reasons, right? And why would those reasons be? So one is that your data usually looks more like that, right? Like it's not ever completely friendly in a nice CSV format. You have missing values, you have nulls, you have floats when there should be integers, you have education statuses that maybe aren't correct. And it also comes in a variety of sources. So you might have XML files that you need to parse, or you might have tables in a database, or you might have JSON that's coming in as streaming data. And then also there might be other features or combinations of features that would be incredibly useful to include that aren't necessarily in the original data set. So the amount of money that a person has in their bank account would be incredibly useful as a determinant to whether they would pay me back. But that wasn't included in the original data set. So I, as a data scientist, or you as a machine learning engineer, would have to go to your boss and say, hey, I have a hunch that this would be incredibly useful information to include. So is there a way that we can go out and find this? And then you would need to think, how am I going to merge it with the original data set of anonymized values? Like what is the primary key that you can use to identify Joe who's asking for a loan, right? So traditional machine learning can be extremely, extremely effective, and it requires less hardware than deep learning usually because your data sets are smaller, your algorithms are less complex, but it also requires a lot of work up front, and it's useful for well-defined specific tasks mostly where the data is alphanumeric, so where it's words or it's numbers. And the data science lifecycle is also extremely iterative. So we tried one thing and it seemed to work really nice, but that might not have been the best model to select. And we might have had better performance if we had changed some little hyperparameters, if we had done little tweaks in our original code. So what we've talked about thus far in the data science lifecycle has been data acquisition and cleaning of it. It's been a little bit in terms of modeling, and it's been a lot about business understanding. But really, that's just kind of like the tip of the iceberg of deploying a data science solution in production. So it's extremely useful, but it's also something that you need to do with very much, with a lot of care and a lot of practice. But why most of us are probably here today is because we heard some really cool buzzwordy things about deep learning in Harvard Business Review or MIT Tech Review, right? And this is the one that makes me the most excited. So artificial intelligence, big bucket, been around for a while, since 1950, 1960. Machine learning, a subset of artificial intelligence, been around since 70s, 80s, 90s. Like United States Postal Service has been using machine learning for handwriting recognition since the 90s, right? Deep learning, subset of machine learning, focused on deep neural networks and kind of new technologies that help you understand massive amounts of data very quickly, massive amounts of complex data. So you're no longer restricted to alphanumeric, even though it's pretty good at alphanumeric stuff too. So what does that mean? It can do things like recognize entities and images out of the box. It can recognize specific humans with just like 5 images for its training set. It can detect cancerous tumors and cancerous cells in X-rays, again, with just very little training data. If you give it a bunch of text, it can do things like spit out representative samples. So this is kind of a joke example of what would happen if you gave all of the Harry Potter books to an RNN, and it would pop out something like Harry Potter and the portrait of what looked like a large pile of ash, right? But again, even though this is a toy example, you can do things like give rap lyrics in the form of William Shakespeare because you've trained it against all of his plays, or vice versa, so William Shakespeare's words end up sounding like Tupac. Like it's really, really cool what you can do with minimal amounts of code and just a lot of training data with tagged formats. You can also do things with sound. So Magenta is a project from TensorFlow where you can make music and art using machine learning. You write a melody or you strum out something on your guitar, and it gives you a drum accompaniment and like a bass accompaniment and all the other bits of music that you could ever hope to have. You can do things like speech to text. So whenever you upload a video to YouTube, it automatically gets transcribed and closed captioned. And that's not because there's like a human on the back end somewhere frantically typing. It's because you're taking the speech and you're automatically turning it into English or whatever language it happens to be. And there was also a great demo at Build, which is one of Microsoft's conferences, where you can do real-time me speaking in English, getting turned into text English that's then translated to Mandarin and spoken out again. So speech to text, text to speech in a different language, or even taking the speech that I'm saying and turning it into a visual display of sign language, right? Like that's incredible to me, and it opens up so many doors if you can have that real-time processing. And there's a whole heck of a lot more too. So the Sudoku solver this morning was awesome. AlphaGo obviously is amazing. Being able to do style transfer, so taking a Van Gogh painting or Picasso painting and juxtaposing it on top of the Mona Lisa. Autonomous driving, obviously, but lots and lots of use cases. Really, we're only limited by our imagination. Like there's a professor from Stanford, very, very popular, Andrew Ng, who said that anything a human being can do in 1 to 2 seconds, so any classification that any of us can do, deep learning should be able to do now or in the next year, right? So that's kind of, just think of that. Like anything that it takes you 1 to 2 seconds to do can be potentially automated away with deep learning. And it's every industry. So it's there's no industry that's safe. Like people were trying to think of one at Stanford a few years ago, and they initially thought something like hairdressing. But even that, like optimizing scheduling, optimizing the amount of dye that you use for each hair client, like all of that can have deep learning applied. And it's become so popular recently because it's more accurate than humans at classifying images, at language translation, at voice and sound. So if everybody in the room started talking and I wanted to pick out somebody from the back, it would be difficult for me to do it myself, but deep learning would be able to do it in a snap. Also, we have specialized hardware, so things like FPGAs, which are field programmable gate arrays, or GPUs, or custom ASICs, so custom silicon-like TPUs, tensor processing units, which are Google's technology, or Google's chosen technology. And what that is basically taking the algorithm for TensorFlow or for any of the other deep learning frameworks that you've heard about and kind of burning it into the silicon so that you get absolutely the best performance that you can possibly have for TensorFlow. Field programmable gate arrays are a little bit different in that they have less energy expenditure, I believe, but they're also more flexible in that you can use them for a variety of frameworks. So it's not just like that it's not just, out of the box, great for TensorFlow. You can use MXNet or PyTorch or whatever you want. And we also have lots and lots of data, right? But that's kind of an obvious thing. Sensors are everywhere. The data acquisition is only going to accelerate as we advance more. And I would also like to add, all of the open source is fantastic. So, firm commitment from companies, from humans, to support things like scikit-learn, like TensorFlow, MXNet, PyTorch. And then also the ability to use it on massive kind of democratized cloud infrastructure as well. And if you wanted to get started with artificial intelligence, there are really a couple of options that you have. You can either create your own model or you can deploy somebody else's. And if you're creating your own model, it takes a lot of time, It takes data, it takes experience, and it takes hardware. So time, usually weeks to months if you have a considerable data set. And that's just like that's after it's been created, right? Like so often very, very large scale models like the ones we have at Microsoft, they take weeks to run. So not even counting the time it takes to build the thing, but like once you hit go, it takes weeks to train on all of the data that we have. Data, millions of classified inputs, so millions of tagged things. Experience, so machine learning engineers, and we are not cheap, right? And we're also apparently very hard to find. So that might not be the most wise thing for a startup to have on staff. And then also hardware, so things like GPUs, TPUs, FPGAs, etc. And GPUs, I'm not going to go super in depth on this because I think I'm running a little bit below time. But you would use a GPU because the way that it's architected is fantastic for neural networks. Neural networks, you have a bunch of layers with a bunch of nodes in each layer, and basically all of the nodes are doing the same thing. And that's idealized for a GPU. For a CPU, they're really good at sequential processing. So at doing one thing and then doing another thing and then doing another thing and then doing another thing kind of in a row. GPUs are really great at taking a lot of similar things and doing them all simultaneously, right? So you have a CPU. Whenever you end up with instructions that are all the same, it calls a GPU, and then when the GPU is done, it sends it back to the CPU, right? And TPUs, FPGAs, quantum computers, whenever they're a thing in reality, they're all going to operate the same way. So it's like you have your CPU doing the sequential stuff, and then when you have a bunch of tasks that are kind of the same, you send it off to that specialized architecture hardware, and it comes back, and the CPU does its stuff again. So that's why you would want to use a GPU. FPGAs and ASICs are basically GPUs on steroids. So GPUs, very performant, and they're kind of ubiquitous now. FPGAs and custom ASICs, they're a little bit harder to get started with, but they accelerate your projects even more than a GPU would. And the Azure ecosystem around all of this is pretty substantial. So something that I'd like to show you today is called a data science virtual machine. We also have deep learning virtual machines that are data science VMs with graphics cards. And what this guy is I'm using something called X2Go. So you see here that I have five different VMs off to the right that I can connect to. And this is a VM that's been spun up on Azure with a bunch of resources, and you can see that I am very cluttered. But think of it as like a laptop in the sky, right? Like it's just a machine that you've provisioned, and a lot of resources have been automatically downloaded to it. So all of those wonderful open source packages that I was mentioning before, if you don't want to have to worry about managing them and managing all their dependencies, if you don't want to have to worry about taking care of all of the different versions of Python, all of the different versions of Scala, all of that, then it makes life much, much easier. And you can see here that there are a ton of environments that have been installed. So Python 3 with Spark on HDNSite, Python 3 with Spark Local, Python 2 with HDNSite and Spark, RSpark, lots and lots of different things. And you also have, out of the box, so just by provisioning this guy, a lot of notebooks that can teach you things about any framework that you're interested in. So here are 6 that are devoted to TensorFlow. And again, these are Jupyter notebooks like that example that I was showing you before with the decision trees. And all of them are kind of ready and waiting and free to teach you how to do deep learning and machine learning if that's something that you would like to do. In data science virtual machines, my boss would probably not like for me to tell you this, but they are free for the first year for the first $200. And they are available to be provisioned from Azure as on kind of the free services tier. Am I out of time?
No, you're good.
Excellent.
So we've got a little bit of time, but I wanted to make sure folks had a little bit of time to ask a couple questions in case there's any questions in the audience.
Absolutely.
So as you're wrapping up, maybe if folks have questions, just flag me.
Cool. And so I am sorry that I'm running out of time. I will post this on my Twitter. So if anybody wants to have a link to it, it'll be there. But it's something that I created that shows you all of the services that we have on Azure, and ways that you can go about getting started with them. One thing that I would like to mention very specifically is that if you don't want to train your own model, you can do something like, so if you have an idea, you have a favorite movie and you want to put emoji masks on the characters based on their emotion, or you have a great idea, bless you, where you want to put puppy faces on people because that's what venture capitalists fund, or Harry Potter faces on babies, or you notice that your friends are kind of dancing funny and kind of look silly, and who else looks silly? Politicians, and you want to put politician faces on your friends. All of those things sound very difficult, but they're actually quite easy because deep learning models have already been created to do those tasks. So whenever your computer does automatic detection of faces, it's using kind of deep learning frameworks that have already been created. And a bunch of my coworkers have open sourced these projects. They're not just for images, they're also for text. So this is an example of a chatbot that uses natural language processing that's just pointed in an FAQ page to a website. And 2 of those examples are on the screen right now, less than 10 lines of code for each. And I will also post links to these guys. It's pretty amazing the amount of insight that you can get from images, from text, from video, from everything. So with that, I would like to open up the floor for questions. And thank you so much. I hope this was useful.
Good. So we've got a little bit of transition time here as we switch from one to the next. If anybody does have questions for Paige, and then Emily, we can go ahead and get you all switched up while we're going. One thing that I know that we talked a little bit about in your abstract, and maybe you can go into some more detail, is the CI/CD pipeline.
Absolutely. So the CI/CD pipeline for
Oh, and maybe, I don't know if there's a way to do that with, well, maybe that wasn't the best question to ask.
So this will be the last example. But the pipeline for data science is you have data ingestion, you have data, thank you. You have data ingestion, you have data processing, data cleaning. Then once that data has been cleaned by data engineers, it probably gets handed off to data scientists or machine learning engineers to build out those models. Once the model's been created, then it's given to a team of software developers potentially who would refactor it into Java code. And then after all of that's done, so you've seen all of that trade-off, you have to have a DevOps process for taking care of that model. So retraining it over time, making sure that it's still doing what it's supposed to, and refreshing it with data as well, checking to make sure that the data is in the same format. And all of that is kind of available as an open source framework, either TensorFlow Extended, TFX from Google, or Uber is also open sourced a framework for it as well, called Michelangelo. But I personally really like TensorFlow Extended. And if you have questions about putting it on Azure, we've got a POC and I would be happy to talk to you about it as well.